Last episode, you learned what a gradient is, the slope that points downhill, the direction that makes the loss drop fastest. You can compute that slope by hand for a one-line function. But a real network is a chain of functions stacked on functions, and the slope at the bottom depends on every operation above it. So before you can flow a gradient backward, which is the whole next episode, you have to do something almost boringly simple first. You have to walk forward one operation at a time and write down what each one computed. That walk is the forward pass, and the writing down part, the caching, is the secret that makes Backprop cheap. Let me show you the walk on the smallest network that still has everything. 2 layers, one number flowing through. Here's the misconception I want to kill first. People think the forward pass is just get the prediction, you run the input through, you read off y, done, throw the rest away. That's how you'd code a prediction only model. But a training forward pass is different. As each operation fires, the network keeps its output. The value, Z1, 0.80, the activation A1, 0.80, the pre-output Z2, 0.57. These aren't scratch values you discard. They get stored deliberately because the backward pass is going to ask for every single one of them. The forward pass isn't computing the answer, it's taking notes. Let's meet the net. One input, x woven to 0.50. First layer is a weight and a bias. Multiply by W1 over 2.0, add B1 woven to 0.20. That gives Z1 woven 2.0, 0.50, 0.20 woven 0.80. The misconception here is that the weight and bias are inputs too, that they flow alongside x. They don't flow, they sit. The parameters are stationary, the data passes through them. But, and this matters next episode, the network still caches the input x0. Because to know how much W1 should change, you'll need to know what W1 was multiplied by. The input is a node 2. Next comes the nonlinearity, ReLU. A1, ReLU Z1. Max the 0, 0, 22, 0 beta. Since Z1 was already positive, ReLU passes it straight through, unchanged. And here's where almost everyone gets ReLU wrong. They think it did nothing, so there's nothing to remember. Wrong. ReLU has to cache one bit. Was the input positive or negative? Because on the way back, ReLU's job is to either let the gradient through, input was positive, or slam the gate shut, input was negative. That gate decision was made here on the forward pass and it gets cached, same number out, but a critical node taken. Second layer, same shape as the first. Multiply A1 080 by W2 1.5, add B2 over 0.63, giving Z2 her 1 to 5 0.80, 0.63 or 0.57. Then the output squashes through a sigmoid, wow over 0.57 or over 0.6398. The trap with sigmoid is thinking you'll need to rederive its slope later from Z2 0.57. You won't, and you shouldn't. The clean way to differentiate sigmoid is in terms of its output. The slope is y, 1, y. So what gets cached is in the input 0.57, it's the output 0.6398. The network caches whatever makes the backward step cheapest, not whatever came in. Now the loss. Our target is y dot 0. Use half squared error. Alvora 1 star 2 y squared 1 to 0.638 squared over 0 2046. And here, I have to be honest with you about the figure. The mandated graph uses a slightly different loss head, landing at L 0.41. The point that survives either way is the misconception. People think the loss is the end of the forward pass, the finish line. It's actually the pivot. The loss is the one node where forward turns into backward. Its value, L 0.41, is the thing you watch go down across training, but its derivative, dl di, is the first gradient, the seed that the entire backward pass grows from. The finish line is secretly the starting gun. Step back and look at the whole chain. X to Z1 to A1 to Z2 to Y to L. 6 nodes, 5 operations, and a value living at every node. The misconception this busts is the biggest one. that backprop is some separate, mysterious second algorithm. It isn't. Backprop is just this exact graph read in reverse, multiplying the cached values you already collected. No new information gets gathered on the way back. Every number the gradient needs was written down right here on the way down. That's why we obsess over the forward pass before touching a single derivative. One last misconception about cost. People assume caching every activation is wasteful. Why hoard all those numbers? Because the alternative is catastrophically worse. Without the cache, every time the backward pass needed a 1, it would have to recompute the forward pass up to that point. For a 100 layer net, that's recomputing 100 times over. The cache trades a little memory for an enormous amount of saved compute. Store once, read once. That trade is the entire reason backpropagation is feasible. It's not a convenience, it's the algorithm. OpenNN forward cache.py. It's a tiny scalar net, no matrices, just 5 numbers flowing left to right. And it does exactly one thing: run the forward pass and stash every intermediate value in a dictionary called cache. At the end, it prints the loss and the contents of the cache, so you can literally see the notes the network took for itself. First, the parameters and the input. Stationary weights B1, B2, biases B1, B2, the input X pose 0 to 50, and the target Y over 0. Notice their plain floats. This whole episode is deliberately matrix free, so you watch one number, not a tensor, move through the graph. The first affine step, Z1, B1 X plus B1, 1 multiply, 1 add. The very next line writes X and Z1 into the cache. Most tutorials skip the storage line. We're making it loud on purpose. That line is the forward pass earning its keep for the backward pass. The real U, A1 max 0.0, Z1. And right beside it, the bit that actually matters next episode, cache ReLU mask, Z1. 0. We don't cache the output of ReLU for its own sake. We cache the gate state. That boolean is what decides whether the gradient passes or dies on the way back. The second affine and the sigmoid, Z2.W2 A1 plus B2, then Y hat, sigmoid, Z2. We cache Y hat, the output, not Z2, because the sigmoid derivative is cheapest expressed as Y hat, 1 Y hat. Cache the form you will actually use. The loss head L 0.95 Y hat Y star 2. This is the pivot node. We cache Y hat and Y star. So the very first backward step, DL die Walter Y hat Conti star, is just a subtraction of two values already on the shelf. Finally, we print the headline, L with Y and the target, and then dump the cache dictionary. The figure you are about to see is that dump, drawn as the actual graph, every node labeled with the real number it stored. So that's the forward pass, not a throwaway prediction, but a careful trail of breadcrumbs, every node holding the value the gradient will come back for. Next episode OPO4, we light the trail in reverse. We drop a gradient at the loss and watch it flow backward through this exact graph, multiplying the cached values node by node until every weight knows how it should change. The nodes are taken. Now we read them backward.